The Solow model of economic growth emphasizes the role of physical capital per worker in explaining differences in output work per worker in various economies or within an economy over time. So it's based on this model of the production function where we have capital per worker on the x-axis and output per worker as a function of capital per worker. So this production function that we're familiar with that has diminishing returns to capital and therefore is not a straight line but rather this concave line. Okay, so this line that I just drew is just the production function. Okay, and the Solow model relies on the following equation. It tells us that the change in capital per worker from one period to the next depends on the difference between investment in physical capital per worker and depreciation of the existing capital per worker. So how much the capital our workers have is deteriorating versus how much is being put in to replace that deterioration, and then if there's anything left over, create new physical capital for our workers. So this is going to be positive, meaning that capital per worker will be growing if investment is more than enough to offset depreciation. It'll be shrinking if investment is not high enough to offset depreciation, and it'll be exactly equal to 0 when investment is just the right amount to offset depreciation but not higher, and therefore there won't be any accumulation of physical capital. So now let's draw the investment portion on our graph and the depreciation portion on our graph. So investment is defined as some constant fraction of the output each worker is creating. So for instance, we could have this fraction gamma be equal to 25% of output being reinvested into new capital. So the y here, output per worker, okay, this is just this line here. So if we're taking a constant fraction of that entire line of output per worker, it's just going to be a line that is a little lower, 25% the amount of the output function that we drew initially. So then let's draw the second piece of our equation up here, the depreciation part. So depreciation is going to be defined as delta fraction of our existing capital stock. So for instance, delta might be 5%, and so that means that 5% of the capital per worker is depreciating each period. So here, if we draw this depreciation on our graph, we want to draw a line that represents some fraction of capital per worker. So this k, this little k, that's what's on our x-axis. So we're just going to have a fraction of k. So this will be 5% of k. And so this would be a line with a slope less than 1 because 5% is less than 1. So let's draw that in here. It's going to be a straight upward sloping line because 5% is a positive number. So we have depreciation is a constant fraction of what's on our x-axis, which is capital per worker. Okay, so now we can actually go back, now that we've drawn this, and review these three scenarios in our graph. So the first scenario has investment greater than depreciation. So if investment, which is the blue line, is greater than depreciation, then our capital stock is growing, right? And that happens anytime we're to the left of this intersection. Investment will be greater than depreciation. And anytime we're to the right of this intersection, depreciation is greater than investment. And so we're in this scenario where the capital stock is shrinking. So let's add that to our graph now. Right, so let's label this intersection because that's clearly important. I'm going to label it KSS, where SS stands for steady state, and we'll revisit that meaning in a moment. Anywhere to the left of steady state capital stock, investment is greater than depreciation, and therefore capital per worker is growing. So if we start out, let's say here at K1, then investment next period will be greater than depreciation, and so the next period the capital stock will be bigger, and so on each period until we get to the steady state capital where investment is just exactly equal to depreciation, and therefore there's no change in capital stock. The money being invested into capital is just offsetting the depreciation, and there's nothing left over beyond that to grow the capital per worker. In contrast, if we're anywhere to the right of the steady state capital, then investment is less than depreciation. Right? We see that in the graph. Here's depreciation. It's higher than investment anytime we're to the right of the intersection. Okay, so the capital stock per worker would then be shrinking because investment isn't even high enough to offset all of the depreciation. And if we start out in a situation to the right of the steady state, let's call it K2, then we would see our capital stock per worker shrink every time period until we get to the steady state. So now let's actually mathematically solve for the steady state level of capital stock, and from that we'll be able to also determine, once we know KSS, we can determine what the corresponding steady state level of output per worker is. So we'll call that YSS. Okay, so solving for the steady state level of capital per worker is very straightforward. We rely on the definition of steady state, which tells us that the change in capital per worker in steady state is equal to 0. Okay, so applying that, we would say, all right, well, in steady state and only in steady state, delta K, the change in capital per worker, is 0. All right, so that means that investment equals depreciation. So I'm going to go over to the next slide, give ourselves some room. So we're solving for steady state, which means investment is equal to depreciation. So that means our gamma fraction of output that's being invested each period is equal to our delta rate of depreciation of our existing capital per worker. All right, well, Y is actually equal to some function of capital per worker. So recall for the Solow model, we're relying on the Cobb-Douglas production function, which tells us that output per worker is equal to this equation, where the A is a productivity parameter, so it's just some number. Let's we can assume that's 1 for this example, but we'll leave it in for now as a symbol. Capital per worker, and then alpha, it's raising it to the alpha power, which in practice is usually about 1/3, but we'll leave it as a symbol. Okay, so plugging this equation in for output per worker, right, we have investment here per worker is equal to depreciation of capital per worker, and then we just solve out for K, and that'll be our steady state level of capital. So we can start by moving the K over here and the delta over here, so we get gamma A divided by delta is equal K to the 1 minus alpha, right? This is like K to the 1. We're dividing by K to the alpha, so that turns into K to the 1 minus alpha. Then to get rid of the 1 minus alpha exponent, we raise both sides to the 1 over 1 minus alpha. And that leaves us with just K on one side, and this is our steady state capital per worker. So now we can plug in for the numbers that we had assumed in the previous slide, and we need to make a few more assumptions. So we're going to assume that A is just equal to 1, that productivity parameter, and alpha, we're actually going to deviate from the data in the real world just to make the math work out a little more nicely, get some nice round numbers. Rather than assuming alpha is a third, we're going to just assume it's a half for now. And then plugging in all those numbers, we have an investment rate of 25%. A is 1, delta is 5%, and then all of that is raised to the 1 over 1 minus alpha. So let's see, 1 over 1 minus alpha is 1 over 1 minus a half, which is 2. All right, so we end up with 25 as our level of capital per worker, okay, in steady state. And then we can plug into the production function for output per worker to determine the steady state level of output per worker. So remember, this is our Cobb-Douglas production function. So A is 1, so we're just left with K in steady state, which is 25, and we raise that to the alpha power, which we're assuming is 1/2 for this example. So that's just the square root of 25, which is 5. So output per worker is 5. Capital per worker is 25 in the steady state. So again, we can draw this here on a small graph. We have capital per worker. On the y-axis, we have, again, output per worker, but also really investment per worker and depreciation. We have output per worker using our Cobb-Douglas production function and the assumptions we made about different parameters. We're assuming looks like this for this example. Investment per worker, we're assuming for this example is 25% of output per worker. And then depreciation per worker is 5% of capital per worker. The intersection between investment and depreciation occurs right here. So this is steady state, K steady state, which we solved for as being equal to 25. And then we plugged that back into the production function and solved for output per worker in steady state equal to 5 units.